Hi there! Welcome to Wonder Maths. I am Katie Guillermo and today's episode is all about the different wallpaper groups. First off, what is a wallpaper? Well, it is a type of pattern that requires at least two translations in different directions. A wallpaper pattern covers the whole plane and can be mapped onto itself by translations in more than one direction. For a plane figure to qualify as a wallpaper pattern, it must have at least the basic unit, one copy of translation, and a copy of these two by translation in second direction. That is, there must be at least two rows with each one at least 2 units long. Here are some examples of wallpapers. You can see them everywhere. It may be as a decorative paper for the walls of a room, or a decorative background image that covers the desktop of a computer or a mobile device. So how are patterns on a wallpaper even made or generated? First, have a motif that will be repeated to make the pattern. Second, reflect the motif horizontally. Third, rotate it by 90 degrees. Fourth, reflect about the axis that is 135 degrees counterclockwise from horizontal. And lastly, translate the unit vertically and horizontally. So now you ask, what are wallpaper groups? They are a mathematical classification of a two-dimensional repetitive pattern, whose patterns are categorized by their symmetries. And here are the 17 distinct wallpaper groups. So to help you know and understand that not all wallpapers are the same and that there is mathematics behind it, I'm going to discuss them further for you. CM. There are no rotations in this group. However, it contains reflections and glide reflections with parallel axes. The translations may be inclined at any angle to each other, but the axes of the reflections bisect the angle formed by the translations. So the fundamental region for the translation group is a rhombus. PM. This has neither rotations nor glide reflections, but it does contain reflections. The axes of reflection are parallel to one axis of translation and perpendicular to the other axis of translation. The lattice is rectangular, and the rectangular fundamental region for the translation group can be chosen, that is split by an axis of a glide reflection so that one of the half rectangles forms a fundamental region for the symmetry group. PG has neither rotations nor reflections. However, it contains glide reflections. The direction of the glide reflection is parallel to one axis of translation and perpendicular to the other axis of translation. And the lattice is rectangular as well, similar to the group PM. P1. This has no rotations, reflections, and glide reflections. It consists only of translations. The two translation axes may be inclined at any angle to each other. Its lattice is parallelogrammatic, so a fundamental region for the symmetry group is the same as that for the translation group, namely, a parallelogram. The PMM's largest rotation order is 2, and it contains perpendicular axes of reflection. The lattice is rectangular, and the rectangle can be chosen for the fundamental region of the translation group so that a quarter rectangle of it is a fundamental region for the symmetry group. The CMM also has the largest rotation order of 2 and perpendicular reflection axes as group PMM. The centers of the rotations do not lie on the reflection axis. The lattice is rhomic, and a quarter of a fundamental region for the translation group is a fundamental region for the symmetry group. The PMG contains both a largest rotation order of 2 and a reflection. The centers of rotation do not lie on the axis of reflection. The lattice is also rectangular, same as the group PMM. The PGG's largest rotation order is 2, and it contains no reflections, but it has glide reflections and half-turns. There are perpendicular axes for the glide reflections, and the centers of the rotations do not lie on these axes. And again, the lattice is rectangular. P2 has a largest rotation order of 2, and there are neither reflections nor glide reflections. The two translation axes may be inclined at any angle to each other, and its lattice is parallelogrammatic, where a fundamental region for the symmetry group is half of a parallelogram that is a fundamental region for the translation group. P3M1 has the largest rotation order of 3 and contains reflections. The axes of the reflections are inclined at 60 degrees to one another, and all of the centers of rotation lie on the reflection axis. Its lattice is hexagonal. P31M is quite similar to the previous one, where it also contains reflections, a largest rotation order of 3, and a lattice that is hexagonal. However, only some of the centers of rotation lie on the reflection axis. P3 contains a 120-degree rotation, that is, a rotation of order 3, and a lattice type of hexagonal. In P4M, the axes of reflection are inclined to each other by 45 degrees, so that 4 axes of reflection pass through the centers of the order 4 rotations. In fact, all of the rotation centers lie on the reflection axis. The lattice is square, and an eighth of a square fundamental region of the translation group is a fundamental region for the symmetry group. P4G's largest rotation order is 4, and it also contains reflections, but the axes of reflection are perpendicular, and none of the rotation centers lie on the reflection axis. And again, the lattice is square. P4 has a 90-degree rotation, that is, a rotation of order 4, a lattice that is square and has no reflections. The centers of the order 2 rotations are midway between the centers of the order 4 rotations. The P6M group contains rotations of order 2, 3, and 6, as well as reflections. The axes of reflection all meet at the centers of rotation. At the centers of the order 6 rotations, 6 reflection axes meet and are inclined at 30 degrees to one another. Its lattice is hexagonal. P6 contains 60 degrees rotations, that is, rotations of order 6. It also contains rotations of order 2 and 3, but no reflections. Its lattice is hexagonal. Once again, there you have it, the different wallpaper groups. Here you can see the difference between the different groups by showing only a single motif with different reflection axes and rotation orders. Thank you so much for tuning in. I hope this helped you a lot, and until next time!